Hello students, welcome to Misostudy video classes. Now today we are discussing a topic that is from the previous chapter that is exactly is going on, that is mechanical properties of solids. Fine. So today it is a turn for a very important aspect of that particular phenomena of mechanical properties of solids. Now if you try to recall, we started our discussion with Hooke's law and Young's modulus and so on so forth, but still we not discussed anything associated with energy. So today we are going to discuss that thing. Fine. So before that I would like to start this discussion with a simple example, that is Poisson's ratio. Fine. What exactly this topic is basically? Sometimes maybe in 2 marks they may ask it, or sometimes in a reference they may ask it. Fine. So I thought it is better to share these simple questions, because for your school exams 1 marks, 2 marks, 3 marks, they all are important questions. So what exactly the Poisson's ratio is? With the help of one simple diagram I am going to show you this aspect of Poisson's ratio. Basically it is the name of the scientist, it is not Poisson, fine, it is the name of the scientist. So let us say from this you can say a type of stand, a wire is hanging, fine. So let us say this is the wire. This is a thin wire, but I am creating it slightly bigger so that you can visualize it. Now obviously the wire is in the shape of a cylinder, fine. So for this wire there are 2 important aspects. One is its length, you can say L, and another is its area, okay. Or in more polished fashion I can say area of this circular cylindrical wire is something that is governed by its radius, fine. So important is not area, important is radius. If radius will decrease, radius will increase, accordingly area will increase or decrease. So I think I should also mention it that important is radius, fine. So now I have basically 2 parameters, one is length, another is radius, fine. So let us make it more beautiful by writing only this radius, fine. This way, this is radius r. Now do one thing, I have some weight and the weight is hang with this end, fine. So when either we are hanging some weight or simply we are trying to pull this wire downward. Ultimately if we are putting some force at this free end, so what will happen? Length will increase, first thing, but we are missing something. If its length will increase, then its radius should decrease, fine, and that is something that we are missing. So when force is applied at free end, fine, then now 2 things are taking place. Then number 1, L increasing, okay, and number 2, R, I think small r, okay, no problem, R decreasing, okay. So now put aside stress, but here 2 types of strains are present, fine. Just because of these 2 parameters 2 strains are present. So 2 types of strain present. Okay. This statement is separated by this statement. Fine. So, I hope now the things are simple and also clear to all of you. Now, there are two types of strain, one is lateral, one is longitudinal. So, number one, longitudinal, O-N-A-L, longitudinal, that is delta L by L, and another is lateral. Okay. Both are strains, but one is longitudinal, one is lateral. Lateral is this minus delta R upon R. Why minus? Because one is increasing, another is decreasing. Now, Poisson's ratio is PR, that is Poisson's ratio is this 1 by 2. Fine. So, ultimately 1 by 2 means dimensionally meaningless, L. Fine. So, I can say Poisson's ratio is nothing but a number. Okay. And what is the value? So, that I would like to mention here as the value is, there are two types of values associated. One is mentioned as theoretical value, another is mentioned as practical value. So, theoretical value is minus 1 to 0.5. This is the theoretical value of Poisson's ratio, and another is practical value. Practical value is 0 to 0.5. So, this is the idea of Poisson's ratio and its expression, and then this value. So, there are two values, this is theoretical and another is practical. Now, it was a subtopic. What exactly the main topic of today's video is? That is elastic or twisting potential energy. Fine. So, now I am coming on to our actual topic, that is, for this explanation I think I should clean this green board and then I will explain you what exactly the idea of this elastic energy. Fine. So, that is the idea of our topic. Elastic energy. Basically, the name of this topic is elastic potential energy. Fine, because no motion as such is involved over here, but this is sufficient. Elastic energy. Now, what is elastic energy? If I have an option to squeeze or twist any object, then I am doing some work. It means against the molecules of that particular object. Say for example, I have this marker pen. Now, if I am applying a force in its twisting, it means the molecular arrangement of the plastic of this pen I am trying to disturb. So, I am doing some work. Now, it is going to be stored in this. So, that is something which is defined as elastic energy. Now, let us say still you are unable to understand it. So, let me explain you with the help of one more example. Let us say I have this wire. Fine. Obviously, if I am holding a load or pulling this wire downward, fine, like this. So, what will happen? I am trying to increase its length, means I am doing something against the molecular arrangement of this wire. So, I am doing some work, and this work is defined as the elastic potential energy of this wire. Fine. If I will stretch this wire, then heating will produce. This is something that you can really experience with some careful arrangement. You take a copper wire and two, you can say a specific type of devices to hold the wire and then try to pull it. Be very careful like these with these type of experiments. Or if I am twisting something, say for example this plastic duster, if I am twisting this duster, then I am doing some work and that is going to be stored. Fine. So, this is the idea of elastic potential energy. Simple is squeezing or twisting any object. Fine. That will we give you the idea of this elastic potential energy. So, important terms are here: twisting or squeezing of any object, It means what? We are doing something against the molecular setup. So, molecules will be disturbed. Fine. Okay. Molecules will be disturbed. So, we are doing some work against their arrangement and this is something which is defined as elastic energy. Now, if this idea is clear, so I should pick up an example and then gradually I should show you how this is something that you can visualize. Okay. So, with the help of one diagram which I just created few minutes back for the explanation of Poisson's ratio, I will use that diagram. Okay. But before that I show you a graph, and with this graph I started the discussion of this topic basically. The graph is like this. It is U, energy, molecular energy. Fine. And this is distance r. In solids that we are discussing right now, there is a specific arrangement of molecules. Okay. So, let us say for example, this is molecule A and at distance r this is molecule B. So, interatomic forces are acting, intermolecular forces are acting, because we are talking in terms of molecules, sorry for that atomic. So, intermolecular forces are acting, they are holding them together. Now, the graph plotted for this energy and this distance is somehow like this. Okay. This is R naught, this is R1, this is R2. Fine. Now, negative, this is 0, it is positive end, it is negative end. Negative energy max means what? Binding energy. So, all these are bind together. Now, you can easily find out if the distance between the molecules is increasing. As R is increasing, so this energy is decreasing. Moreover, if the distance between the molecules is decreasing, then also the energy is decreasing. And for a specific value which I mentioned with R naught, the energy is maximum. So, if I am squeezing or I am twisting, I am doing something with this R, I am disturbing this R. So, if I am disturbing the R, either I am going towards R1 or going towards R2. So, energy is going to reduce, negative energy will reduce because I am providing some work in and in terms of that energy. So, ultimately that excess energy positive is going to be considered as elastic energy. Okay. Now, let us try to drive a relation with the help of a simple example. Okay. And the example is this way. Once again I have a stand this way, and with this stand I attached a wire. The wire is not very thick, but just to show you properly I am creating this big wire. Okay. Once again the same concept, that is, it is the initial length of wire and it is area of the wire. Fine. Now apply a force F over here. So what will happen? Now the second thing, actually it will happen, so this is something that I would like to show you with the help of a next diagram. What will happen? The length of the wire will increase, obviously it will increase. So earlier length was capital L, now the length is how much? The length is L plus delta L, say for example. Fine, enhanced length. Obviously area will vary, and let us say this difference in length initial to this is going to be, I think I should not mention it over here, simply say it is L prime, otherwise few people will get confused. Let us say L prime, and one thing is clear, L prime is more than L, very much clear from this diagram. Let us say the overall increment is x, say for example, this increment in the length. So this increment in the length we can classify in small intervals, that is this portion, say for example, that is delta x, another portion that is delta x, like this, total this distance. Fine. Now obviously if I am applying a force downward and increment in the length of the wire is taking place, so I am doing some work against these molecular forces, and that work is going to be stored over here. Fine. So there must be some work done by me, by the agent. So that expression, that idea I am going to expand over here. Fine. So F elastic, basically I was about to write down F external because I am applying, but in terms of this entire setup, if I am writing F elastic, then you will not be confused, because you know, yes, elastic means from Young's modulus. Fine. So F elastic, it is equal to what? Young's modulus was y is equal to F upon A whole to the upon delta L by L. So this F elastic, if I am removing, then finally I can write it down as y A x upon L. Fine. I hope you will not find any difficulty in understanding this term, general relation. Let us say it is equation number 1. Fine. Now from here I should talk in terms of energy. So this external energy, external is equal to minus W elastic is equal to delta U. Same thing, same idea, same concept, but with all other different possibilities. Either this electrostatic potential energy change or work done by elastic force, W suffix elastic. Fine. Do not get confused, this is W Wales, it is not the name of a cricketer, it is simply elastic basically, and this is external because the force is external. Fine. So let us talk about these small intervals. So for small interval dx, small work done is dw, and we consider initially with for small interval, and then we will expand it for the entire this wire. Fine. So for small interval, dx. Okay, for a small interval dx I can write down dw is equal to y-ax upon L into dx. I hope you all will be comfortable with this particular equation. Fine. Next is net W is what? Net W is 0 to L. That complete enhancement, L, X, capital L, small l, L prime. I mean, you have to just consider what exactly is happening. These symbols are not a boundary. Fine. So, 0 to L dW. Now, if you will put this value of y-a-x upon L over here, take out all constant terms out of the integration and integrate, you will get the result. But wait for some time, I am not jumping for that. Once again, I would like to summarize this diagram and this graph, because what is happening on, if that is clear, then this all is not so difficult. Otherwise, this integration, this diagram, all things are going to be complicated. That is why I picked the example of this duster, this wire, just to give you a feel what exactly is happening. So, once again, now in totality, take the look of both these diagrams. This is a wire. Now, let us talk in terms of slightly polished language. Molecules have a specific arrangement in this metal wire. I will not explain that. When we are applying some force, then length of the wire is increasing, means molecular setup of this wire is disturbing. These wires, in this wire the molecules are bind this boundary. So, that potential energy is given as this way, it is negative because of molecules of the metallic wire are not free to move anywhere outside of this wire. As you keep on moving in reduction of this distance between the molecules, disturbance is going to come. As you come to decrease the distance, disturbances, means movement you are doing some disturbing phenomena with the molecules like chhed-chhad, you will find yourself in a difficult condition. So, that difficult condition, because we did this, so we are in a process to elaborate it. Now, I am here for the explanation of this work done. Okay. Now, dW is y-a-x-l dx. Fine. So, W is equal to y-a upon L 0 to L x dx. I hope things are clear to all of you. Now, integration is very simple, x square by 2. Fine. That is W is equal to y-a by L, fine, y-a by L into x square by 2 0 to L. Fine. It means, let us put the value, so you will get L square by 2. So, W is equal to, now it is nothing but arrangement of the terms, nothing else. So, I am arranging the terms, half y L by L in one bracket, in another bracket, because I already placed the values. So, it is going to be A L. I hope the terms are clear. Half y A by L, A, yes, L square, fine. Now, there is a specific meaning of all these terms, y L by L, L by L, yes, y A and then A L, okay, one more A L, yes, there is a simple arrangement. So, just arrange the terms like this, 1 by 2, yes, then y L by L, y L by L, fine. Then next term is small l by capital L, find small l by capital L, and then AL, yes, because you can cancel this capital L with white wala, this capital L, fine, and then you can arrange the terms. So now students, every term has its own meaning. What exactly? This term is known as stress, while this small l by L is defined as strain. And beautiful part is that this A into L is nothing but it is volume. Now why I am writing it like this? Because this is now going to be the part of your video. Moment you will watch this type of arrangement, you can easily understand that what exactly the meaning of each and every term. So what you can say, this energy W is what? Try to recall this work energy power chapter, that work done is what? That is delta U is equal to W is equal to half stress strain, fine. And if I am removing this volume, so what I will say, it is the electrostatic potential energy per unit volume, fine. That is why I am not writing this volume over here. So it is half stress into strain volume, so per unit volume. Otherwise you can put it half stress into strain into volume, it is up to you. In numericals, if it is asked like this, you can easily understand and use this relation, fine. So students, in this particular video I explained the idea of what exactly the concept of Poisson's ratio, and then this elastic potential energy. By squeezing, enhancing, twisting, anything is possible, but ultimately what you are doing, you are playing with the arrangement of the molecules, okay. So I think in this video we should stop over here, but this concept is very important for school exam point of view, for derivation and for all these things. So I hope you will follow one of my simple advice, that you will keep revising, keep enjoying. So very soon I will come back with a new video, but till then take care of yourself, keep revising, keep enjoying, have a nice time. Thanks a lot.